Hello guys, my name is Desmond and I welcome you on my lesson for today, ladies and gentlemen. So we'll be looking at interpretation of graphs. Okay, remember guys, on our previous lessons we started with vertical projectile motion in one dimension, where I was taking you through the introduction of this chapter, and then we did a lesson where we define the concepts of vertical projectile motion in one dimension, and then we also discussed vertical projectile motion equations, and I also took you through some steps to using those equations. Okay, so now what we're doing is the interpretation of graphs. As soon as we're done, then the next lesson will be doing some practice questions. Okay, finally, when we conclude with this chapter, that's when we solve exam papers. Okay, ladies and gentlemen, we're almost done with this chapter, and I hope you've been enjoying the previous lessons. Ladies and gentlemen, at all times, I always say a day without learning something new, it's a day wasted. Okay, so please do make sure that at all times you learn something new out of my lessons. And most importantly, ladies and gentlemen, please do make sure that you do not just start by watching this lesson, but please do make sure that you start from the first lesson, because as you continue with some more and more videos, that's where you will have a better understanding, because the previous lesson that I've done, they also contribute towards you understanding the final videos. Okay, very much important, ladies and gentlemen. So now for today's lesson, we'll be focusing on the graphs for motion on horizontal plane. Okay, very much important. So now that means we are only focusing on object. Let's say it's a car. I'm not really sure if it's my marking pen is dying. It could be a car, it could be a boy on a skateboard, and again on a horizontal plane it could be our friend walking either in that or that direction. In all situation, ladies and gentlemen, it doesn't really matter in which direction, but what matters the most is that we're dealing with objects in motion on a horizontal plane. Okay, not objects moving vertically up and down. As soon as we're done with this lesson, ladies and gentlemen, I'm going to also start a special lesson where we focus on objects either being projected vertically upwards or falling from the top. Okay, so for this lesson, ladies and gentlemen, we're only focusing on graphs of motion, graphs for motion on horizontal plane. Okay, so ladies and gentlemen, let me just try to get a new marker. Okay, so the graphs that will be focusing on, it's going to be position versus time, it's going to be velocity versus time, it's going to be acceleration versus time. So those are the three quantities, not necessarily the three quantities, but the three types of graphs that we'll be looking at. Okay, and the first type is where we've got an object which is stationary. Okay, obviously we know, ladies and gentlemen, for an object which is stationary, it means the velocity is 0. Okay, and then another type is the second one. If you're not able to see over there, this is constant speed. Okay, so that means we're going to draw the graph of position versus time, velocity versus time, acceleration versus time, where an object is at stationary. Okay, ladies and gentlemen, again we're going to have three types of graphs of that versus time, that versus time, that versus time, where the speed is constant. And these are the graphs. I've already drawn them, so what I'll be doing is to explain to you each and every graph. Okay, very much important, ladies and gentlemen. And again, we're going to draw the graph of position versus time, velocity versus time, acceleration versus time. Ladies and gentlemen, for an object which has an increasing speed. Okay, so these are the graphs. This is the graph for position versus time, graph for velocity versus time, graph for acceleration versus time. And lastly, ladies and gentlemen, we are also going to talk a little bit more about a position versus time graph, velocity versus time graph, acceleration versus time graph in a situation where an object is decreasing its speed or velocity. Okay, so these are the graphs, ladies and gentlemen. So I'm just going to explain each and every graph. Okay, very, very much important, ladies and gentlemen. So now let's start with our first graph. Okay, so we'll just start with that one, second, third, and we'll just do the same for each scenario. Okay, so now, ladies and gentlemen, let's focus in a situation where we've got an object which is stationary. Okay, what does it mean, ladies and gentlemen? It obviously means its velocity is equals to 0 meters per second because it's stationary or it's at rest. Okay, very, very much importantly, remember, for objects on a horizontal plane. Okay, very, very much important, ladies and gentlemen. What a beautiful car, guys. What a beautiful car. Obviously, in this case it's stationary, so that means its v is equals to meters per second. We'll also explain for situations where you've got a different scenario where the constant speed is the speed is constant, increasing or decreasing. Okay, very, very much important, ladies and gentlemen. So now let's start with the first graph. Okay, so obviously the first graph is for delta x versus delta time. Okay, so this is the graph, ladies and gentlemen. At all times, this is the position for delta time. In all of these graphs, ladies and gentlemen, the horizontal line represents the time. Okay, remember, most importantly, time in seconds. Okay, I've just explained to you on my previous lesson that time in physical sciences is measured in seconds. So even when you draw on your graph, ladies and gentlemen, make sure that on your problem, time is in seconds, otherwise convert it to seconds. Okay, so again, ladies and gentlemen, you need to remember that we're sketching position versus time graph. So that means we've got a position, we've got velocity, we've got acceleration. All of this is being sketched against time. Okay, so we sketch all of this versus time. That's why we have 1, 2, 3 graphs. 1, 2, 3 graphs. 1, 2, 3, 1, 2, 3, 1, 2, 3 graphs for position versus time, for velocity versus time, acceleration versus time. Okay, I hope you're able to see the similarities in each and every graph. Okay, similarities is that your horizontal or your x-axis represents the time. Okay, very, very much important, ladies and gentlemen. So now what happens on that first graph? You've got a delta t, and then you've got a change in x. Okay, what matters the most, ladies and gentlemen, is that you indicate in brackets that delta x is measured in meters. Okay, so if you were to score some marks, you will be allocated a full mark for indicating that on the vertical axis is delta x, and that delta x is measured in meters. Okay, and again on this side delta t, which is measured in seconds. Okay, so now, ladies and gentlemen, what happens to the distance when a car is not moving? Remember, guys, this is time, so you can say 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds, and so on. Okay, so if an object is not moving, what happens to its distance, ladies and gentlemen? Is the distance increasing Is the distance decreasing or is it constant? Obviously, ladies and gentlemen, the distance is constant. It's not in any way increasing. Okay, very, very much important, ladies and gentlemen. So that's why we've got a straight line in that direction. It means for every second, ladies and gentlemen, the distance, it's not being covered. It's not being covered. Obviously, in that direction, you'll find that maybe it's moving to the right, otherwise in that direction it's moving to the left. But in this case, that object, it's not moving. That's why you've got a straight line. Okay, very, very much important, ladies and gentlemen. A straight horizontal line to indicate that the displacement or the distance, it's not being covered as time goes on. Okay, I'm not sure, ladies and gentlemen, if you fully understand that part, but I suppose it fully makes sense. Okay, so now let's move to the second graph. Obviously, ladies and gentlemen, you have to indicate that this is changing time in second at all times. Now that we are doing velocity versus time, then on this side it's velocity, right, meters per second. Very, very much important, ladies and gentlemen. Say velocity, in brackets, say meters per second. That's the SI unit for velocity, the SI unit for time at seconds. Okay, so in this case, ladies and gentlemen, what is the velocity of that object which is stationary? It's just 0, ladies and gentlemen. Remember, this is the origin. That point is what we call the origin. Remember, on the Cartesian plane, ladies and gentlemen, on the Cartesian plane, so it's more like this is delta time, and then this is this is change, not necessarily change, but this is a velocity in meters per second. This is time in second. Okay, so for this graph to look like this, ladies and gentlemen, we just remove the negative side and also remove the negative side of the Cartesian plane, because it's not necessary for this type of graphs. Okay, that's why we have something like that. So obviously, you know, from a Cartesian plane, this is your origin, this is your 0 point. Okay, so at that point, that's where the time is 0, and again whatever that represents the y-axis is 0, which in this case is the velocity. Okay, so ladies and gentlemen, because that vehicle, it's not moving, it's at rest or it's stationary, so this graph, ladies and gentlemen, it's just like that. Okay, otherwise, if we have a line somewhere there like that, it's more like this a vehicle, it has a certain velocity, because obviously if this is 0, this could be 1, 2, 3, whatever meters per second. So that's why we don't have the graph at all, because that object is not moving, so its velocity, it's 0. Okay, so the line for that, one can say it runs within this one. You can say the velocity is 0 as time goes on. Okay, that's why we say remember, this is time, could be 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, whatever. So as time goes on, the velocity remains 0. Okay, so I hope you understand the reason why for a stationary vehicle, you don't have any drawing on the graph that represents the velocity versus time. Okay, so now let's move to the graph for acceleration versus time. At all times, you say change in t in seconds, then acceleration, it's meters per second squared. Very, very much important, ladies and gentlemen, for you to indicate acceleration and its SI unit, delta t, and its SI unit, you score full marks. Okay, very, very much important, ladies and gentlemen. Remember, guys, obviously, because the velocity is 0, this vehicle is not moving. Okay, if it's not moving, its acceleration is equals to 0. Okay, ladies and gentlemen, that's why in a car you've got an accelerator. What happens when you step on accelerator, ladies and gentlemen? It accelerates. You can feel it increase the velocity. Okay, but in this case, the car is not moving at all, which means there's no acceleration. Okay, there's no increase in velocity. Very, very much important, ladies and gentlemen. I hope you fully understood that part. Okay, so now let's move to the next scenario where the speed is constant. Okay, constant speed. Let's focus on that one, ladies and gentlemen, and sketch the position, velocity, and acceleration versus time graphs. Okay, so now let's start with the very first one. Remember, guys, objects moving at a constant velocity. This is what we are focusing on. Okay, so a constant velocity. Remember, what does it mean when the velocity is constant? From the previous lesson, we just explained that when the velocity or the speed is constant, that means the acceleration is equals to 0 meters per second squared. Okay, very, very much important, ladies and gentlemen, that you watch my previous lessons, because otherwise, if I didn't have to remind you this part, you would be asking yourself, how is it the case that when the speed is constant, the acceleration is 0? That is fully explained in the previous lesson. Very, very much important, ladies and gentlemen. So now let's have a look at that graph. So obviously at all times, delta t in seconds, we start with the position versus time graph. Okay, so remember, guys, now we look at the distance versus a time graph. So now we are dealing with an object which is moving at a constant speed. Okay, so if it's moving at a constant speed, it's just, let's say a car, it's just at that constant speed. Okay, so let's say there's house 1, house 2, house 3, house 4, and so on. This is a car traveling on the street and it's passing houses. Okay, at house 1, let's say it covers 2 meters. It's traveling at 2 meters per second. Because the speed is constant, ladies and gentlemen, it means even at house 2 it should be passing at 2 meters per second. Remember, this is just an example, that speed. Okay, just so that you understand, it could be any value. So let's say maybe it passes house 3 at 2 meters per second. If it passed house 4 maybe at 3 or 2.1 meters per second, then it's no longer constant speed, because when it gets there it has increased. Okay, so for it to be a constant speed, it means it has to be 2 meters per second throughout. Okay, so in simple terms, ladies and gentlemen, we're basically saying for every second it covers 2 meters. That is what 2 meters per second means. It means for every second it covers 2 meters. So when the tick, when the clock ticks and say 2 meters, 2 meters, 2 meters, 2 meters, I hope you fully understand it. That's what we mean when we say 2 meters per second. If it's 40 meters, kilometers per hour, that means for every hours it covers 40 kilometers. That means in 2 hours it's going to cover 2 times 8 kilometers. In 3 hours it's going to cover at another 40. Then it's, what is it? Is it 120? 120 kilometers. I hope you fully understand what it means by something meters per second. Okay, very, very much important, ladies and gentlemen. So now let's see. So that means for every second it covers a certain distance. For every second it covers that same distance. For every second, same. Another second, same. Another second, same. By same, ladies and gentlemen, I'm talking about the same distance. Okay, Very, very much important, ladies and gentlemen. So now that means if you represent this graphically, you will say this is for every second it covers that distance, and then for the next second it covers that, for the next second it covers that, for the next second it covers that. Okay, for the next second it covers that. Okay, very, very much important, ladies and gentlemen. That's why this graph, it has that straight line. Okay, because it covers the same distance, the same distance, the same distance, the same distance for every second, for every second. Okay, hope it makes sense, ladies and gentlemen. That's why for a graph of that versus that under a condition where the speed is constant, you've got a graph similar to that. Okay, so this prepares you in a situation where you have been given this graph and they ask you the questions based on that graph. Okay, we are going to do more of we're going to solve more questions, different questions where we'll be facing different scenarios. It's very, very much important that you join me in those lessons so that you don't miss out. Okay, delta t in seconds. Now I'm just going to move a bit faster, ladies and gentlemen, because I've already explained the importance of writing that in the units. Okay, so in this case, ladies and gentlemen, the speed, it's constant. Okay, remember guys, now we are on velocity versus time graph. The question is, if a car is traveling at a constant speed, what happens to its speed? It means it's not changing, it's the same. So let's say it has a certain amount of speed. Okay, so that speed, is it increasing, is it decreasing, or is it the same? Ladies and gentlemen, I hope you fully understand. So guys, because it's not increasing, then we remove that type of a graph. Ladies and gentlemen, because it's not decreasing, then we remove that type of a graph. Ladies and gentlemen, very much important. That's why we've got that type of a graph, which means for every second the speed is the same. Okay, for every second the speed is the same, of which it could be 30 meters per second. So throughout it will be the same. So that means this could be 10, 20, 30, 40, 50, 60. Okay, that's why when we talk about an increasing speed, you might find that the graph is like that, because as time goes on, its speed is increasing. Okay, very, very much important, ladies and gentlemen. I hope you fully understand that part. Okay, so now let's focus on the last one, changing t in seconds, which is acceleration meters per square second. So ladies and gentlemen, remember, I've just given you a hint to say the acceleration is 0 over there. So as time goes on, the acceleration, it's not increasing, it's not decreasing, it's just 0 because the speed is constant. Okay, so ladies and gentlemen, I hope it makes a perfect sense. Okay, just be happy if you now understand as compared to when you were seeing this, in the beginning of this lesson, where you just saw those graphs and you didn't have an idea of how to interpret those graphs. But now I'm hoping you're having a better understanding. Okay, so ladies and gentlemen, let's now go to that one where we're dealing with an increasing speed, increasing speed of velocity. Okay, so now ladies and gentlemen, we're dealing with an object which is moving with increasing velocity. Okay, this is what we call non-zero acceleration, constant non-zero acceleration. Okay, so by constant non-zero acceleration, ladies and gentlemen, obviously remember we're dealing with objects moving on a horizontal plane. Okay, so obviously this object or this car, whatever that it could be, it will be moving in that direction, increasing its velocity. So as time goes on, ladies and gentlemen, as time goes on, its speed is increasing. So you'll find that maybe when it passes house 1, house 2, house 3, whatever. When it gets to house, let's say at house 1 it was passing at 30 meters per second. At house maybe 7 it's now 120 meters per second. At house whatever, maybe house 30, it's now maybe at, just as an example, it's at 200 meters per second. Okay, so now we're going to sketch the graphs of an object moving with an increasing speed or velocity. Okay, so ladies and gentlemen, it's that first graph over there. Let's have a look, guys. Obviously it's delta t over time, and then this is change in x, which is in meters. Okay, so ladies and gentlemen, as time goes on, that object, it's covering it's covering long distance at a shorter space of time. Okay, I hope it makes sense, guys. Remember, I'll just try to indicate to you that this is a car moving at at a speed which is increasing over some time. Okay, so I'm just going to count in seconds, and you notice what happens. So as I draw a line, that is the speed covered over the ticks, which will represent the time. So ladies and gentlemen, this is the first second. Can you see, ladies and gentlemen? It started slowly. The time is ticking constantly. It's just, can you see, ladies and gentlemen? So that means it's increasing its velocity. Okay, so you find that for the first 1 second it covered that distance. For the second second, ladies and gentlemen, it covered that distance. Okay, so you can see this distance, this distance number 1, it's a bit shorter compared to distance number 2, and the next distances will be longer and getting longer and longer and longer. Why? It's because it's increasing its speed. Just think of a car, ladies and gentlemen. It starts from 0, it increases, it increases, it increases. As it increases its speed, you cover long distance over a short period of time. Okay, so that is why, ladies and gentlemen, a graph, it takes that kind of a shape. Okay, why? It's because for every second, ladies and gentlemen, for every second, for the first few seconds, the distance covered, let me just do something like this so that maybe it makes sense. Let's say this is 10, 20, 30, 40, 50. Okay, 1 second, 2, 3, 4, 5, 6, 7. So it's more like on the first second it has covered that distance. On the second second it has covered, let's say, maybe approximately 5 seconds. Then on third second it covered 10 10 meters. On 4 seconds it covered that distance. On number 5 seconds it covered that. 6 seconds it covered 20. That it covers on 6 seconds, it has now covered, this is 40, 50. Obviously on 7 seconds you'll find that it has covered maybe 90. Can you see, ladies and gentlemen? As time goes on, it covers more distance. Okay, that's why the graph is like that. What influences that to be in that shape is because the speed is increasing. Okay, unlike a constant speed, okay, where a graph might look something like that. Ladies and gentlemen, I hope it makes sense. Okay, remember, if it doesn't make sense and you feel like there's something which is confusing you guys, try to replay this video at least 3 times, and then from there, if you still don't understand, you can just drop me a WhatsApp. Okay, otherwise you can just comment on this video. Ladies and gentlemen, let's now move to that one where we focus on delta t in seconds. We are now on velocity, which is in meters per second. Okay, so ladies and gentlemen, what happens in a situation where the speed is increasing? Okay, ladies and gentlemen, over time, remember these are just the seconds, okay, and then these are just the speed in meters per second. So for every second, okay, for every second, what happens to the velocity? It's also increasing. Okay, ladies and gentlemen, I hope it makes sense. This is different from a speed which is constant. Okay, in this case it was 10 meters per second. It was 40, 50. Okay, so on the first second its velocity was 10 meters per second. At 2 seconds its velocity has increased. Okay, it's now 20. At 3 seconds its velocity has increased. It's now 30. 4 seconds its velocity has increased. 5 seconds its velocity has increased, and so on. Okay, that's why it takes that shape. Okay, so ladies and gentlemen, this is for an increasing speed. Very, very much important, ladies and gentlemen. So now let's have a look at the acceleration, which is in meters per square second, delta t in seconds. Okay, so now ladies and gentlemen, in this case, what happens? Remember, we are at a stage where the speed is increasing. Okay, so as time goes on, ladies and gentlemen, as time goes on, the acceleration, okay, the acceleration will be at at some point. For example, because the speed of this object is increasing, then it means it's accelerating. Okay, it's accelerating. I hope you fully understand that part, ladies and gentlemen. So that dot, it can't be at 0, because the moment we put it at 0, it's more like that object is at rest. Okay, but for the fact that we say it's increasing, then it's at a certain value. Okay, so the acceleration remains constant throughout. Okay, it can only be at a different point if maybe the acceleration is now or maybe the rate at which the speed has increased is different. Okay, let's say maybe it's increasing at 20 meters per second. Okay, the speed for every second it increases at that. Okay, so you might find that maybe the acceleration is there, but now if it's increasing at 40 meters per second, you might find that the acceleration is up there. If it's increasing at 80, the acceleration maybe is up there. Okay, but what matters the most is that the graph remains the same. Okay, so I hope, ladies and gentlemen, you've got an idea of what I'm trying to explain. Okay, all of this will make a perfect sense when we solve the problems, but for now you just need to be aware that we've got a graph which might look like that. Okay, so now let's focus on a decreasing speed. Okay, an object decreasing its velocity. Okay, so ladies and gentlemen, for an object which is decreasing its velocity, we've got those types of graphs. Okay, so ladies and gentlemen, obviously we start with the position versus time graph. So we'll say change in x, and then this will be changing y in seconds. Remember at all times to write the units. Okay, so ladies and gentlemen, what happens when an object is moving on an horizontal plane, on a horizontal plane, and is decreasing its velocity? Okay, obviously is the opposite of what we had in a situation where we had an increasing speed. So ladies and gentlemen, if you can compare these two graphs, you will notice that it's just the opposite of what we drew. Okay, so ladies and gentlemen, that is because over time, because it's decreasing its speed or velocity, over some time it will cover longer distances within a short space of time. So it was actually moving at a higher speed. It's now decreasing its speed. Okay, so what does it mean? It was maybe let's say traveling at not necessarily, not comment on the speed but the distance. To say initially it was covering maybe 2 meters for every 1 second, and then as time goes on, maybe after 5 seconds, let's say this is 2, 4, 6, 8, it's 8. Okay, so this is 10. Okay, so can you see, ladies and gentlemen, this is, let's say for example, 4, 3, 2, 1. Okay, so can you see in 3 seconds, in 1, 2, 3 seconds, okay, in 3 seconds it has covered 1 meter, because let me see, this is 10, it has covered 2 meter. This is distance, ladies and gentlemen, 8, 9, 10. Okay, so in 3 seconds it has covered 2 meters. Okay, whereas when you compare it on this side, in one let's say in 1 second, let's say in 1 second it covered what is it, no, let me just do that, because that point is actually somewhere there. Okay, so it's more like in 1 second it covered 2, 4. This is obviously 2. So in 1 second it covered 4 meter. So can you see, it was actually driving at a higher speed, but that speed is now starting to decrease. Okay, so obviously, ladies and gentlemen, while it was traveling at a higher speed, it was covering longer distance within short space of time. Ladies and gentlemen, I think it makes sense. Just when you think about it, that's when it makes a perfect sense. Okay, so I hope you understand why the shape looks that way. Okay, so ladies and gentlemen, let's now focus on let's now focus on that one, which will obviously be delta t in seconds, velocity in meters per second. Okay, so in this case we are focusing on the speed or the velocity versus time. So obviously for a decreasing speed, ladies and gentlemen, that means initially it was moving at a certain speed, okay, which could be 40, it could be 100. The reason why you don't have values there, it's because it could be any number. Okay, so the direction of the graph tells whether that number is increasing or decreasing. Okay, so obviously this is also time in seconds. Okay, this is also time in seconds. So it means as time goes on, its velocity is decreasing. Okay, why is it taking that shape? Is because the values going down are decreasing. Remember, this could be anything. Okay, could be 20, 40, 60, 80, 100 meters per second. Okay, so if we drew this graph in that direction, it was going to be as if as time goes on, its velocity is increasing. You understand? But in this case, as time goes on, its velocity is decreasing. That's why the shape of that graph is in that manner. Okay, ladies and gentlemen, let's now have a look at the last one. Okay, so ladies and gentlemen, this is where we've got that graph of acceleration, which is in meters per second squared versus time, which is in seconds. Okay, so remember, ladies and gentlemen, in this case, because the speed is decreasing, that's why you've got acceleration on the negative side of that Cartesian plane. Okay, so remember, obviously because it's decreasing, then it means it's decreasing. I mean, it's already in motion but decreasing. That's why it starts at a certain point and not there, because if we have a dot there, it's more like it's not moving. Okay, so but in this case it's moving but decreasing. Okay, that's why you've got a constant line over there. I've explained it there. The only difference in this case is that this is for when the speed is increasing. Okay, but this is for when the speed is decreasing. Very, very much important, ladies and gentlemen. So guys, I hope you fully understand all that I tried to explain to you guys. So ladies and gentlemen, thanks very, very much for joining. I hope to see you on my next lesson, where I teach you the graphs for objects moving vertically up and down. Guys, my name is Desmond and I'm out.